Start recording. All right, good deal. Now, yep, I get the thing that tells me it is being recorded, so now we're being recorded. So this will be available for those later on. All right, folks. So let me talk a little bit just about sort of the way the online stuff works. It's a little different, obviously, a little more disconnected, right? Can't see me, which is worse. I am going to try to get that camera problem fixed. I was telling some folks a few minutes ago, it does see the rear camera, which faces my wall. Another thing I thought about doing was putting a mirror up, and then I thought, oh, geez, then everything's backwards. So I'm just going to kind of, I put in a trouble ticket thing to find out what's wrong. It's not my camera on my computer because it does work in other programs. So unfortunately, there's no video, at least for this one. Hopefully it'll get it fixed. But don't let that stop you from interacting with me. And again, you can interact with me chatting. You can put something in the chat box. And don't worry, like in class, for a pause. Don't worry about, in other words, interrupting me. I'm pretty good at kind of keeping an eye on the chat box, and if you say something to me, good morning, Raymond. Good morning. If you say something to me, I can usually find a spot to stop. If I don't stop right away, I'm waiting for a convenient time to stop, but I'll definitely get to answer your question or your response or whatever the case may be. You can also talk to me, like I said, just chat it in, say, hey, I need to turn on the mic, or like I said, you can raise your hand. You can share video with me too. That does sometimes lag things down, but if you wanted to show me something, then we could certainly share video. As I said earlier, I wouldn't be able to show you me. I could just show you my wall, but I guess I could make that work. What else do I need to say? I think that's it for that. Do y'all have any questions for me? I was saying earlier, it looks like there's a bit of a lag, and the way I can tell that is I'll chat something, and it seems an inordinate amount of time for you guys to respond. So if it seems like I'm getting impatient, it isn't that. If I, it's more because of the fact that I'm not aware of the lag. But let me see. I'm going to text y'all something. Give me some response back when you get it. So I'll just say, because it's all messed up. So I just texted you something. So when you receive it, give me an emoji, or I don't type in a period. Yeah, okay. All right, that's not so bad. All right, good deal. Okay. First of all, before we get started, I was looking at some videos. I'm always fascinated by waves. I studied marine biology, but I've always been just fascinated by the size and the power of waves. And I watch these guys hitting these big waves, these surfers that do like those 90-foot waves off Portugal. I'm thinking, man, I could never do something like that. I don't have the balance to be a surfer, and I just don't have the guts to do something like that. Excellent, thank you. But anyway, I was also looking through some other stuff, and I was talking to you guys the other day. So now we get ready to get into class. So I was talking to you guys the other day about adaptation. We were talking about evolution, and we were talking about what Darwin was discussing during his theory of evolution was the fact that organisms aren't going to survive unless they can make it in their environment, right? In a simple way of putting it. So I was thinking about that, and sometimes what I'll do in lectures, I will step back for a second, like I'm going to do that today a little bit, to kind of cover the gap, or like maybe go over something again. So many times after classes, I'm walking in my office, I'm like, man, I really wish I'd done that a little different, or something like that. So sometimes if I think there's some confusion, but really no confusion here, but an interesting curiosity. This is a picture. It's an electron micrograph, an electron microscope picture. And I love these things because they take everyday, ordinary objects and they magnify them with electron microscope, and you're like, what the heck is that? Like, I'll have one later on. I think I show it to you guys. I show it to my bio too, of what the head of a straight pin looks like under an electron microscope. It's not anything. It's not straight. It's not pointed at all. It's kind of flat at the tip, which is really kind of interesting to think about. Yeah, kind of. It's got that fluffy sort of thing to it. This is what we call a cross section. So imagine they took a loaf of bread and sliced it in half, right? So this is a cross section through a polar bear hair. We talked about mammals and the fact that they all have hair, right? And that hair does lots of things. And one of the things that hair does is it keeps us warm, right? And if you think about a polar bear living where they do, keeping warm is a probably important thing to do. It's not so much that they have hair, right? Look in the middle. Look at, I can't draw when I'm sharing an application because you can usually draw on the screen, but you can see the hole. It's more of an oblong shape. polar bear hairs, right, are hollow. They're hollow. They're tubes. That's not found in other mammals. If you were to look at a cross section of our hair, for example, it would be hair all the way through. There wouldn't be the hole in the middle. So think for just a second about what it's like to live in a cold climate. Think for just a second what maybe a hollow hair might give you a benefit over a hair that isn't hollow for a polar bear. You know, use those. You're not seeing the picture? You do have it now? Okay. Okay, good. So think for just a second. Can you come up with again, what I was talking about in class yesterday, using those critical skills of things you already know. Maybe living in Florida, you don't know it as well, but if you've ever been up north or been in the cold, you'll know the proper way to dress. Like if you're a hunter and you're going out during the winter, you're going to know the right way to dress to keep yourself warm. So think about that. Any idea any idea why the adaptation for polar bears to allow them to live in cold climates, that's adaptation, means that they have hollow hairs. What's the significance of the hollowness to the hair? Any idea? Cooper's choking on a bone. Cooper, slow down. Okay, but okay, part of that's too, yeah. But now, okay, how do all of those things keep them warm? There you go. How does that work? Remember, living organisms are governed by the laws of physics. We're governed by the laws of chemistry. Those laws were around before there were living things. If you jump off a cliff, just because you're living doesn't mean you ain't going to be affected by gravity. So think about it physically. And again, think about how you would dress if you're going into a cold area and how that relates to having hollow hairs. And of course, like you say, keeping them warm. And Raymond, I'm glad you mentioned that because that is another thing that allows them to do. How does fluffing up hair, even if it's not hollow hair, how does that keep you warm? If you're a scuba diver or you know about scuba diving, why do they wear wetsuits? Or how does a wetsuit keep you warm? There you go. There you go. So the hollowness of the hair, right? That's like having that's an insulating layer. When you go into a cold climate, how are you supposed to dress? If you're going out into the woods for half a day or whatever, or you're going camping out there, how are you supposed to dress to keep yourself warm? Other than, warm clothes, I understand that, but yeah, there you go. You got it, right? So when you said the fluffing up, there's a layer. So the hair, man, I wish I had my camera because I'm using my hands. The hair, when it fluffs up, traps the air next to the skin, right? It's not permanent, right? I mean, it's not like a balloon traps the air, but it does. That takes a little longer for the air molecules to move through the hair when it's fluffed up, okay? So that means that the body temperature, this is a mammal, the skin temperature, the skin warmth is going to warm the hair. That's what a wetsuit does. A wetsuit lets a little bit of water into the suit, and then your body warms that water, and that's why you stay warm. Anybody that's ever done any scuba diving, and I've done quite a bit myself, will tell you one of the ways you can stay warm when you're getting cold when you're scuba diving, because you lose heat a lot faster in the water. And again, that water in your suit is going to be replaced, but it's going to stay in there long enough to warm up. But everybody will tell you one of the ways to stay warm is be in your wetsuit, right? Then you can open the suit and flush it out a little bit, but it keeps you warm, okay? So not only does the fluffing up do that, but like Tim says, the layering. What does he mean by layering? Well, you got hair, air, the tube, right? And then hair again. If you think about air flowing through that hair. So that's an insulating layer. So when you go out and you go hunting, that's part of that layering that you do, right? What you're trying to do when you stay warm, folks, with a coat, one or two or however many, is you're trying to trap the air next to your body. It's just like a wetsuit. You're trying to trap air versus water next to your body so it warms up, right? Okay, so again, it's not permanent like a balloon, but you understand how that works? Insulating. So what I would say is, as the cold air on the outside of the polar bear hair, right, and the warm air that's being generated in that layer you mentioned next to the polar bear hair, what's going to happen is when they meet each other, they're going to kind of mix together. So the air that touches the skin is not going to be quite as cold as it out there in the air. So let's say it's minus 10 degrees Celsius, minus something or other Fahrenheit, 20. I don't do the conversions. I just think in Celsius. So if the air is minus 10, next to your hair might be, or next to your skin under that layer might be 0. They think, hell, that's pretty damn cold. 0 is still 32 degrees Fahrenheit. It's freezing, right? But, staying alive sometimes is a matter of just a couple of degrees. So maybe that extra 10 degrees is what allows you to survive. Insulating is the effect that that keeps them in layers. All right? It keeps the cold out, keeps the warm in. They do mix, but you understand what I mean? So that air next to your skin, yeah, it's not going to be as warm as if you were standing in the tropics, right? If you took a temperature probe and put it right down on the polar bear skin, my guess it's still like maybe 0 degrees, right? They have other things that prevent them from freezing, by the way. In addition to animals that live in climates like that, believe it or not, in their blood have antifreeze. Isn't that cool? Many fish have antifreeze in their blood, so they can live in water that's freezing. But you got this insulating layer here, so that hair down next to the polar bear skin might be, again, 0 or 1 degree Celsius. But on the other side, I think the skin in this picture is probably on the left, the darker brownish area. But on the other side where there would be the air, it would be, like I said, minus 10. Same thing your house does with insulation, right? And you can do that with hot and cold. I used to have a Siberian Husky that, as a pet, and people would say, oh my goodness, doesn't the poor dog just die in the heat? And it was so weird because I would think so too, right? But Sasha used to lay in the backyard of my house in the sun and take naps in July. And I'm like, holy cow, why doesn't that dog die of heat stroke? Well, if you think about it, in that case, the hair was kind of preventing the skin from getting quite as hot as the air. So if the air was, let's go Fahrenheit, right, 97, maybe next to your skin it was 92. It's still pretty hot, but for some reason Sasha was okay with that. All right, let me, there we go. Okay, now I'm stopping sharing. Let me go to the slides. You guys are more than welcome to make comments, or if, or if you need clarification. I find biology so fascinating that I want to be appreciative of the fact that I know that for some of you who aren't biology majors, it's kind of one of those, oh, really, blah, blah, blah. I get that. It's kind of the way I felt maybe in some, although I found most of my classes pretty interesting. But I just want to show you that there's wonderment, there's amazement everywhere, no matter what you like to try to study. So, all right, let's go back to this. Yeah, have you taken a physics course, Raymond? Actually, you'll get a little bit of in this class. Do you know about diffusion? Okay, so diffusion says that things move from a higher concentration to a lower concentration. If you think about that in a real micro level, really down at the molecular level, let's say now down at the heat level, that since the skin of the polar bear is warmer than the air, yes, heat is being lost to the environment. The heat is kind of like this diffusion thing. You're going to go from where it's warm to where it's cold. Warm things cool off, cool things warm up, right? That's heat. That's how the energy, that's thermodynamics. That's how that works. So what that means, though, from the sense of diffusion that's happening is, yes, the polar bear skin is cooling off, but it might be just a few degrees warmer closer to the skin, and that could be the difference. Global climate change, folks talk about, global temperature change. Many climatologists, and global climate change is not disputed by any serious climatologist. 97% of climate scientists out there said yes, that human beings are contributing to global climate change. But we're talking about temperatures sometimes changing only a range of 1 or 2 degrees Celsius and having these profound effects. So don't think that the polar bear is going to have to keep its skin at least like 90 degrees Fahrenheit. It's not going to do that. Like I said, that skin down there is probably still pretty cold, but just warm enough, right? Mother Nature, adaptation, evolution does not say organisms have to be perfect, okay? She says that organisms have to be good enough for the environment they live in right now. Absolutely, by all means. While Raymond's typing his question, what I would like to do is kind of step back into this inductive, deductive reasoning. I hope you guys have downloaded that sheet. Oh boy, think about animals that don't have hair. Name an animal that doesn't have hair. Pick any animal that doesn't have hair. Never had hair, so don't throw in the whales. So go back again to, let me go back into the chat. Sorry. I missed your question then initially. Does that mean that an animal with solid hair doesn't stay as warm as efficiently? Correct. Okay, but among a mammal, which is a warm-blooded critter, right? Staying warm is usually not the problem. Okay, you can get too warm, and actually you could go back to insulating just like Sasha did in the backyard. But staying warm with a warm-blooded critter is usually not the problem. It's not getting cold that's the problem. So you might find this kind of special adaptation in a warm-blooded critter that with hair living in an environment in which one of the really strongest pressures is staying warm, right? Maybe not such as big a deal. Like for one thing, down where it's really warm, say in Africa, if you're a mammal, it's getting too hot, go jump in the water. Assuming an alligator or crocodile's not going to eat you. Love the questions. Does that make sense, Raymond? Or beginning of it anyway? Cool. Yeah, absolutely, please. The questions are all part of this. Don't think for a minute you can't do that. So as I was saying, we talked about deductive and inductive reasoning. I hope you've downloaded that worksheet that's in chapter 1. It's the same ones we went over yesterday, and practice those. Remember what I said with deductive and inductive reasonings, they're kind of the opposites of one another. Whereas deductive reasoning, you start with something really big, a theory, the theory of planetary motion, right? From, who was that, Kepler? Yeah, he was the one to describe the way planets move around the sun. Kepler says things revolving around a sun, planets in the solar system, presumably planets and other solar systems, which we're finding. Isn't that cool? It wasn't until 1995 we found other planets outside our solar system. When I was a kid in school, we only know the 9. Now there's, 8, include Pluto. I think that just fascinates me that now we've found thousands of planets out there, and some of them in that Goldilocks zone, right? Some of them in that place not too far from the sun, not too close to the sun, exactly where we are, that maybe there's life. My goodness, to me, one of the most fascinating things is astrobiology. What's life on another planet? Does it use DNA? Does it work the same way we do, right? So you take this theory of planetary motion, back to that, right? And you can make a hypothesis. You can say, I'm looking at some planet way the heck out there in a galaxy going around a sun. I'll bet you it moves the way Kepler's law of planetary motion says it should move. So you observe it, you collect your data, and you go, wow, Kepler's right. Even on some, Kepler didn't see that planet way out there in the middle of some galaxy that we didn't discover till 1995. Okay? But you can use deductive reasoning. That's what we say the logic flows down. Where you take a big statement, da-da-da-da-da, all mammals have hair. I'm running around the jungles of Borneo, and I come across some critter. I come across, I'll show you the critter I come across. Check this one out. This is a primate, okay, so related to you and I, that is found only on the island of Madagascar. All right, let me, okay, I'll do that. Here. I'm sorry, Collaborate has made some changes recently, and unfortunately they actually made it a little bit clunkier. So it's not working quite as well. as it should. Look at this thing. Is that cool? Look how small, too, because look at the person's fingers. Although them claws look like that, maybe that's why she's wearing a Band-Aid. So here you go. You ain't never seen this critter before. I've never seen this. I didn't even know what this thing was, right? But look at the green eyes. They're fascinating as heck. Now, tell me something that you do know about this critter using deductive reasoning, using that theory that says, da 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 da, this big proclamation. Use that to make a prediction about what kind of critter that is. There you go. Beautiful. Both of those are very good observations. Okay? The fact that it's got large eyes, great, Raymond. That's right. Now, eating the fruit, I'd have to look at the teeth. I'm going to assume a tree-dwelling critter here, very small the way it is. You wouldn't last very long on the floor of the forest or wherever it lives in Madagascar, would you? It's kind of like us when the dinosaurs were around. But, Caitlin, you picked up on the hair too, right? It has hair. It must be a mammal. Okay? See how that worked? What is this called, by the way? This critter's common name, come on, mouse. There we go. Is this. Oh, type it in. If you ever were in the Navy, you've been aboard ship, you know that's aye, as in yes, or you confirm. Someone asks you a question, aye means yes. All right, let me go back to my slides for a second. Again, I apologize. This is just a little bit clunky. Back to that inductive and deductive reasoning. I can't quickly switch between what I share with you guys, and that's the change they made, which, of course, change isn't always good, is it? All right, so here's a good example of using some inductive reasoning, right? Let's take a look at all these critters. Now, erase the fact that in the middle it tells you what they are, but you knew what they were anyway. It's not like you didn't know these were mammals. Thank you for my pencil. There we go. But look at all these critters, gars. Oh, African wild dogs. I love these things. They hunt in packs. They get together and strategize. Seriously. You can watch videos of them where they get together and they get ready to hunt this pack of whatever the heck they're eating, you know, some poor gazelles or something, and they get together and they strategize. They're like, 3 of you run this way, hide behind the bush, and then we'll chase the gazelles down that trail, past that bush, and you jump out because by the time we get down the trail, we're going to be tired. That's why dogs many times hunt. That's why hunt in packs, because they get tired. They chase fast prey, so they take. It's like a relay race. Can't run down a gazelle, but if I keep, you know, if I got sections of dogs, one giving off to another, I'll eventually run you down. Cheetahs, holy cow! A guy I saw at a meeting one time put a, it's kind of like the early version of a GoPro. It's called a critter cam. He hung it around a collar on the neck of a cheetah, wild cheetah, and then of course it was anesthetized. Woke up and then there was the video of it chasing things. Think about a cheetah that can run up to 80 miles an hour. Cheetah can do that because if you watch a cheetah run, they can bend their backbone like crazy. They can bend their backbone from here to here. So they can make their feet really stretch. So they can take these long strides. That little critter cam there, cheetah's coming up to 80 miles an hour. Imagine what it would be like. I wish I could find video of this. If you do, please send me the link of the cheetah critter cam, a mere, 18 inches above the ground, booking along at 50 or 60 miles an hour. Very cool, huh? All right, we got to get back to this or we're not going to ever finish the material for the semester. But anyway, looking at all these critters, regardless of how cool and their names are, they are all what? They all have something in common. And therefore, what they have in common makes them all what? Right? Makes them all mammals. So in this particular case, you went the other route, didn't you? Let me go back there. You made some observations. You noticed a pattern. Oh, all them things have hair. I'll bet you all things that have hair are mammals. Now, of course, humans invented mammals. I get it. It wasn't like we went, oh, bing, bing, and the universe said, yes, you got that one right. Those are mammals. We invented mammals. But as a scientific society, as a group of humans, we've decided that we define mammals as things that have hair or have hair, like the whales, okay? So you look at it and you go, hair. I'm going to make a tentative hypothesis. Now, you might go into the laboratory. You might go in the laboratory and you don't find, you find that that's not hair. Hold on one second. Now let's look here. Here is, oh, beautiful, beautiful, right there. Let me share this with you. So annoying that this is not doing it the way it should more, but I just got to show you these things. I'm sorry. All right, take a look at this. So here's the problems we have with reasoning sometimes scientifically. I want you to take a look at this picture. I know it's kind of small, but look down more near, this is an electron microscope picture of an organism's skin, okay? So you see the larger little strands, but look more at the smaller little strands around there. What again, using what we just did with the eye, huh? What kind of critter do you think that is? And everybody can contribute. Raymond, maybe, okay, maybe you're right, and you are, but let's assume that you had no other knowledge as to what that was. If you know the word, you can see the word I typed up there. It's a very strange word, but that may have given it off. But, you know, given that, no, I don't see any reason. I mean, maybe those are flagella, but I'm really kind of looking down. I'm kind of looking down at the fuzziness of the yellow below those larger strands. So ignore those larger strands that look like they're coming out of follicles, okay? I'm talking about, which could be an indication right there, but I'm talking about the smaller little strands. What does that look like to you? Now, what is it, but what does it look like to you? What could you easily argue that looks like? Fur, which is hair, correct? So this is a mammal, right? Based on that data, is this a mammal? Yes or no? Sure. But now, Raymond, you knew it was an insect, or you thought it was an insect. Why did you think it was an insect? While you're thinking of that, I'm going to get back to my other screen. Okay. Any specific? Okay. I love honesty. Hold on, let me get back to the screen. It looks like hair, right? It looks like hair. It is not hair. It is found on an insect. Hold on, I'm trying to do two things at once, and I'm losing my track here. It's found on an insect, so you're entirely correct, Raymond. That is an insect. I don't know what type. It doesn't matter. But the word that was in the tab there, and I'm not going to bother to type it out because I don't care for you to remember it, but what you were looking at, those little furry things, were not hair. They were something called trichobothria. It's not nearly as easy a word to say as hair or fur. Basically, it's they're found on insects. That hairy spider, you might say, oh my God, the thing had hair, it's so big. It looks like hair, but it's really not hair. Okay, observation. This thing has hair. Pattern. Things that have hair are mammal. Tentative hypothesis. That picture we just looked at is the picture of a mammal. Sensory, yes. In insects, absolutely. Also in mammals too, by the way. Whiskers, right? Whiskers are sensory devices. So we can sometimes go through the inductive reasoning and say, well, wait a minute, we got the wrong answer. Why? Well, you made an observation, it fit the pattern. You made a tentative hypothesis that thing was a mammal because it looked like fur. And when you get to the very end, if you make a prediction out of that, you find out that you're wrong, right? It's an insect. What that means is that in science, as in life, there are always exceptions to every rule. Now, that is the interesting thing to me about science, about biology, about all of the sciences together, is the fact that for every 99% of the time, there are the exceptions. I love that sort of stuff. It just shows that there's so much more that we need to learn. For example, why would an insect have hair? Right, it's not hair, I understand, but they would have it for what Beth and Lindsay mentioned, for one thing, could be a sensory structure. They might also use it to stay warm. Okay, well, now, they're not warm-blooded critters, but, when you're a cold-blooded critter, the warmer you are, the more active you are. That's why lizards come out and warm up on the sidewalk. That's why lizards come out and warm up on the sidewalk during the summer, because they're cold-blooded. They warm up from the hot sidewalk, run back into the bushes and chase the insects and try to eat them. That would be a good thing if that picture that we're looking at was, say, of a, I don't know, a spider. I don't know what it was. It was just some Trichobothria. Practice those ones that you can download, those ones we did in class, and get online. You type it inductive versus deductive reasoning, you will literally find what's that big cornucopia? A cornucopia of websites. There are interactive websites. They ask you questions. Which one is this? Which one is this? Okay? So that's part of that self-assessment thing that I was talking about the other day. I think that finishes chapter 1. Let me take a look. Yeah, that's everything I want to talk about in chapter 1. Does anybody have any questions about me before we actually jump into chapter 2, which I'm going to load as we are talking? Anybody got any questions for me? Any problems with Blackboard? Everything's cool? You're just not behaving the way I want you to behave. Anybody else? Everybody's getting signed on. Caitlin and Beth and Lindsay, all are signed on and everything. There's no issues there. Remember, especially in the short semester, we don't have a lot of time if things get messed up. Why are you sharing that? Go. Just a minute. There. Again, I'm sorry, bear with me. There we go. All right. Hey. They should not have gave you a code. I told them not to sell the books with the codes in them this semester. Ay. No, you don't need it. Is it like Pearson? Does it say Pearson? It was probably in the, yeah. No, well, either way, you should take that back because that's $60 and tell them that the book should, jeez, I told them, even look on their website. I'll look after class, but I swear on the website it says that, anyway, it's not y'all's fault. Yeah, go back to the bookstore and tell them you don't even need the code. You just need the book, that's all. Yeah, you can write on the screen too. I don't mind. I mean, you know. You can also, when your name pops up when you're talking, you can add an avatar or a picture. If you want to upload your picture, and that might be nice too, because that way when you're talking, I can kind of get an idea that help me and like remember who you are in class. TE doesn't mean anything, does it? This is some code. Okay, collective groan. Oh, here we are, chapter 2, chemistry. How many of y'all are chem majors? Anybody a chem major? Chemistry. No? How many are bio majors? Like bio majors, not going on to med school, but biology to, you know, like, I don't know, study fish or something or other. No? Trying to find some converts. Every time I get a student to switch to biology, I get a toaster oven. It's from a secret society. I have plenty of toaster ovens. I'm still trying to get some more, though. Okay. Why do we have to talk about chemistry? All right, we have to talk about chemistry. I didn't know it was there. Yeah. Right, exactly. You all get rewards for this. And if it's a female, I get 2 toaster ovens. Because female in sciences, STEM, right, science, technology, engineering, and math, they're rare, so you get more toaster ovens. So any females that want to go into like bio. Now I know many healthcare, and there's nothing wrong with healthcare. Don't get me wrong. But I'm talking about like research biology. Okay, if you jump off a cliff just because you're living, you're gonna hit the ground, right? You got to obey the laws of physics. If you get hot, you got to cool off. And the only way to cool off, like we're talking with the polar bear, talking about sweating the other day, you got to get the hot to the cold. So that's what the water in your skin does when you're sweating. It helps do that. Okay, laws of physics. Laws of chemistry also apply. We are really nothing more than this incredibly overwhelming, I'm so lucky, in the sense that I got fascinated by this stuff when I was about 11 years old, okay? And to me, it's never stopped being exciting. But this incredibly intricate little dance that occurs in a chemical level, just like things that aren't living do chemistry, right? Just like water molecules stick together, or just like gases are formed, and all that sort of stuff, all that chemical stuff that has nothing to do with the living organism. I'm waving my hands like a fool here without the camera. I'm sorry. I should wait. Anyway. All right. But the idea is that these chemical reactions are so specialized, they're so unique that they end up in something a lot, okay, no offense to water molecules sticking together out there, but a lot more interesting than water molecules sticking together. We're actually going to talk about water molecules sticking together later on, but it's what living things do with those that I find fascinating. Okay, chemistry. There's a whole bunch of things out there called elements, okay? An element, do I have the definition? There you go. So you don't have to write that down. It's unique, right? An element is unique. There's only elements are oxygen, carbon. You can't break those down. Well, you can, but then you get protons, neutrons, and electrons, right? Now, all of the elements have protons, neutrons, and electrons. Oxygen, hydrogen, blah, 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 potassium. They all do. Where they differ is in how many they have. Okay, we'll talk more about that later, but that's what makes them unique. You see, an element is a substance that cannot be broken down to other substances. It's not broken down to a substance, okay? It's not broken down. It's broken down into subatomic particles, proton, neutron, electron, and everybody's got those. So there's no uniqueness. Now, in the case of oxygen, which again we'll get to later on, I just happen to know this number, oxygen has 8 protons and 8 electrons, okay? Carbon has 6. So based on that number, you're unique. If you got 6, you're carbon, you're 8, you're oxygen. If you go into oxygen, you take 2 of those protons away, you start with 8, right? Then you got carbon. Okay, more on that later on. All right, what's matter? Anything takes up space and has mass, blah, 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 blah. I love that in a way because it's kind of a philosophy thing. Anything that takes up space and has mass. So things that don't take up space and don't have mass don't exist, right? Kind of a weird thing. I don't know. All right, elements. What are the important ones? Well, up here at the top, oxygen, carbon, what do you got? Hydrogen and nitrogen are important, especially carbon. We spend the whole chapter talking about that. Then, of course, there are some smaller groups of elements. Now, they're what we call, and you go on the A&P, you'll learn more about this. We have these things called essential elements, which means about a quarter of the elements that are essential for life. Mostly it's the ones I got there in red, okay? And they make up, was it 96? Almost 100% of the body mass, 96.3 of your body mass is made up of those 4. A lot of oxygen, a lot of carbon, some hydrogen and some nitrogen, and then smaller of other ones. The essential elements, about a quarter of the elements, that's including that calcium, phosphorus, potassium, and then a bunch of other ones that get lumped into there that are like essential, but only in really, really, really small amounts, like trace elements, for example. You know, like vanadium. I have no idea what the heck vanadium does, but your body needs little bits of vanadium for something. Okay, now what's the difference between, or not the difference, I'm sorry, when you take 2 substances, when you take, for example, sodium here, okay, and you chemically combine it together with another element, so when you take the element sodium and the element chlorine together, so when you get 2 or more elements, all right, then you have a compound. Now it says in a fixed ratio. For example, if you look at sodium chloride, table salt, the atomic symbol, or the chemical symbol, not the atomic, excuse me, the chemical symbol for sodium chloride is NaCl. It's a sodium atom and a chlorine atom, 1 to 1. Okay? Here's another compound. All right? What's the ratio there? You know what a ratio is, you know, boys to girls, apples to oranges. So in this case, every 2 hydro, there's 1 oxygen. There you go. So the ratio is 2 to 1. Okay. Here's a good one. I'm writing it at the top. We'll talk about this molecule a lot later on, but you'll become very familiar with this molecule. What's the ratio? too early to do math. Keep going. You got 3 atoms there. Break it down, Tim, right? Lowest common denominator thing or whatever you call that. Lowest factor. Raymond, you got 3 molecules there. You got the first 2, but what about oxygen? What's its, yeah, there you go. So the ratio is 1, 2 to 1. Okay? Now that molecule that we'll talk about later on, that's glucose, by the way. That's sugar. Oh, okay, no problem. Again, that's part of that lag. Whatever, brother. All right, so 1, 2 to 1 ratio, and that's what we find, right? So that's a compound. All right, any questions on any of that? Okay, I'm going to jump through these things pretty quick. If you get lost, you're confused, or you're like, wait a minute, stop. By all means, say something. I'm going to assume a lot here. You're going to have to help me. Now, if this is, you're listening to it recorded later on, obviously you can't stop me right now, but do get with me and let me clarify it for you. Everybody knows that elements are made up of subatomic particles, or atoms are made up of subatomic particles. And an atom has at least 2 parts. It always has a proton and an electron, okay? And not always, but usually always, it has a neutron. And the protons and the neutrons are found in the middle, which is called the nucleus. The protons are positively charged. The neutrons have no charge. Now, don't worry about what this determined isotope part is. Again, we'll get to that in just a few minutes. The electrons are negatively charged. I forgot a parentheses. They're negatively charged, and they form an electron cloud, a negative cloud. Now, here's where we get a little bit weird and wonky. When you go into the quantum world, when you go into this really, really weird world and where it's very small and you're actually looking at atoms, electrons as little balls like you see in this picture here don't exist. And they do exist. They exist as a little ball and a cloud at the same time. And I'm going to stop right there. Only because, number one, this is way outside the scope of the class. It's way outside of my scope to explain to you. I've read several books on quantum mechanics, and as fascinating as it is, I walk away going, I have no idea what I just read. And it's 8:45 in the morning. So anyway, for our purposes, electrons are little balls. Now, protons are positively charged. Electrons are negatively charged. In this picture, you notice there are 2 protons. This is just an element. This is actually the element helium, by the way. Helium is called helium because it has 2 protons. See there? Determines element. If you had 8 protons, you'd be oxygen. If you had 6, you're carbon. If you're 2, you're helium. You know, the gas that makes that squeaky voice. All right, now you tell me. Based on what we talked about yesterday when we got together, when we talked about balancing and all that sort of stuff, if there are 2 protons, why can it be assumed that that element has 2 electrons? Why 2? Why not 3? Why not 1? Why not 8? Any ideas? Right idea. Homeostasis is a word that we, I'm going to look it up just to make sure that I don't tell you the wrong, but homeostasis is a word that we typically apply only to living things. Let me double check and make sure. Yeah, typically it's something we apply to living things, but you got the right idea, right? And things are going to be in balance. Mother Nature balances things out. For every positive, there's a negative. So just for fun, oxygen, which has 8 protons, oxygen has how many electrons, would you think? There you go. There you go. You got the idea. Right? Makes sense. Things are balanced. Now, I'm a very big stickler. I'm a very big proponent. I'm not just memorizing stuff, but knowing why. So not just memorizing that if you got 2 protons, you got 2 electrons. I want you to tell me why. Because, as you guys have said, they balance out. Okay? They balance out. All right, let's go through a little bit of symbology here so that when we go on in the next few chapters of chemistry, you don't get lost. Here's a little part of that periodic chart that hangs on the wall in chemistry class, and if you're like me, you stared up going, I had no idea what half that stuff is saying. We'll keep it simple for you. Let's not because I'm implying anything that you can't handle it more complicated. We'll keep it simple because that's my level of being able to explain it, to be honest with you. Let's take helium that's in the example that we were just talking about it. Helium has the atomic number 2. Okay. Now, if you noticed in the yellow box, the 2 is at the top. The way it's typically written is in the lower left, like you see in the picture on the right. So we put the atomic number here. Yeah, not on the other side. If there was a 2 on the other side here, that would say there are 2 helium atoms, which, by the way, cannot happen. But anyway, all right. Now, very often, the atomic number is left off, right? You just write He. Why? Because if you write O, oxygen, you know it's 8. If you write He, helium, you know it's 2. It's redundant. You don't need to write it twice. It's kind of like, remember in algebra, you could, you write 2x, whoops, 2x, and then you write x. You don't write 1x, although you could. You understand what I mean? Makes sense? All right, the atomic number is the number of protons. The number of protons is the number of electrons because they equal each other. All of these elements that you see here were formed in exploding stars, which again is physics. It's just incredible to me. The carbon in your body, we're what we call a carbon-based life form. Oh, let's do the exercise first just before we move on. How many protons in carbon? How many electrons? Okay, how many neutrons? Please say you don't know. Oh, good guess. That's right, Tim. Good guess. But based on the information you see right there, are you certain that it's that number, Tim? See if Tim remembers isotopes. That's fine. Is she sitting there with you? Who's your girlfriend? Is she in class, or is she somebody I had in class before? What's your name? Tim's right. That carbon typically does have. Oh, that's right. From class the other day. I'm sorry. All right. Now I make the connection. Of course. All right. Now, Tim and Caitlin / Tim, they were correct. In this particular case, most of the time, carbon has 6 neutrons. Now, we'll talk about that in just a second. Anybody got any questions about the number of protons and electrons? You don't, right? They equal each other out. Okay. How did Tim's girlfriend, guessed correctly? So if we wanted to talk about the carbon that he was describing, the one that's got 6 neutrons, we would indicate it this way. There's carbon, right? I'm not going to put the 6. Why? Because it's assumed. And then in the upper left, now this is a little different than you see in that orange box, but in the upper left there's going to be a number. I'm going to make it easy. I'm not doing chemistry here. I'm doing biology, so I'm going to make them nice round numbers. We're not going to worry about the point blah, blah, blah. So very often when you see carbon, so often that many times it's left off, it's assumed it's what we call carbon 12. Okay? Carbon 12, or that number 12, in the case of helium it's 4 and some change, and the other ones have different values as well, is known as the atomic mass. All right? So elements have a symbol. Sometimes they're replaced, like where is sodium? Sodium in the lower left. Sodium starts with S. We already got an S. It's sulfur, so we make sodium Na. It's natrium, which is like Latin or something for sodium. I can't remember. Anyways, we do that for ambiguity problems. All right, elements have a symbol. Elements have a number. That's the number of protons and electrons. Elements have a mass. Now, if an element varies in its protons, well, let me rephrase that. It can't, right? An element cannot vary in its protons. Why am I saying that? How can I say that elements are not allowed to vary in the number of protons? What happens to them if they do that? Waving my hands again. This is crazy. And what's that mean when you have an atomic? don't get too physics on me here. What happens if I go into nitrogen and I take away a proton? Don't make this overly complicated. It's a different element. Boom. It's a different element. Tim, you're right. It does become charged, and atoms do become charged, but they become charged in an opposite way. I'll get to that in a second. But yes, that's a different element, right? So in the case of carbon there, we look at carbon, and carbon is carbon-6, right? Can't change the number of protons. You do change the number of electrons. We'll get to that in a little bit. Not right now. Hold on just a second. We're just talking about the element as it's born, as it comes out of the star. Carbon's got 6 protons, got 6 electrons. Most carbons got the atomic mass of 12. All right, back to Tim and Caitlin's answer there. How did they know it was 6? Well, since carbon is carbon is always the atomic number 6, you can do it just like that. You can subtract the atomic number from the atomic mass, and the difference is the number of neutrons. Now, I'd rather you know why, though. I'd rather you know why it's 6. I mean, yes, this is a little math trick. It makes it quick and easy. For example, just as practice, let me erase this. Let me go with oxygen. Come on, pencil. Oxygen. The normal oxygen is oxygen 16. How many neutrons in oxygen? Yeah. Okay, now the why behind it, all right? When you look at the atomic mass, and this is the rounded atomic mass, it's not the little bits, because the little bits, the 0.003 that they have in helium there, that's how much it weighs. It weighs 16, okay, it weighs 16, I'm glad you asked that, Raymond, because I forgot to mention it. It weighs 16 atomic mass units, AMUs. So we don't talk about it in pounds and kilograms. We could, but they don't weigh very much. So we make it very standard. And the standard of an atomic mass unit is the proton. The proton weighs 1 AMU. I'm glad you guys are asking questions because it's letting me know, what I need to talk about, right? Protons weigh 1 AMU. Electrons are so light. They do weigh something. That's why, remember that matter? If you don't take up space and have weight, you don't exist. But I'm going to say electrons weigh 0, but I put in quotes. They don't weigh 0, but they weigh so little. That's the 0.003. You can ignore them for our purposes. Now, what you don't know, or what you might not know, is that a neutron also weighs 1 AMU. All right, so going back to how you can figure out the number of neutrons without just doing the simple math, in other words, knowing the why behind the simple thing, is if an oxygen if an atom of oxygen, let me start over, if an atom of oxygen, now we're going to ignore the electrons, folks. They're there, but they're so light, we're not going to worry about it. It's like putting a feather on a dump truck. If an oxygen of atom weighs 16 AMUs and it has 8 protons, then those 8 protons collectively weigh 8 AMUs. Where's the other 8 come from? We're ignoring the electrons. Each neutron weighs 1. There must be 8 neutrons. Now, you might get tricked into thinking that it's always going to be even, and it's not. There's other types of carbon out there, by the way. There's a carbon that's known as carbon, you've heard about that, carbon-14. All right, let's do the trick there. How many neutrons in carbon-14? I was just going to ask that. How come if we change the number of neutrons, it's still carbon? Why didn't it become another element? Raymond's right. It does have 8 neutrons, but how come it's still carbon then? To answer Tim's question. Only the neutrons change. Tim? Yeah, there you go. Remember, it's the protons changing that changes the element. I'm talking about that other particle. I'm talking about the neutrons. You can change the number of neutrons. You don't change the element. You only change the element when you change the protons. Now, there's a name for carbon-14. There's a name for carbon-12. There's a name for all the different kinds of carbon. Most of the carbon in the universe is carbon-12. When it comes out of a star, most of it's made with 6 protons, 6 electrons. Some of it comes out carbon-14. There's even carbon-11. These are all in a not formal way are called species of carbon, but the correct term for them is we say they are isotopes. These are isotopes of carbon. They're elemental atoms. They're carbon. They're oxygen. Carbon's not the only one that does this. The other elements do it, but they're the same element, but you just monkey with the neutrons. That's all. And when you change the number of neutrons, you change how much it weighs. Yeah, that's no doubt. Carbon-14 weighs 14 AMUs, not 12 like normally. But you didn't change the fact that it was carbon, right? Because you didn't change the protons. Boom, boom, boom. Okay, I'll talk radioactive isotopes in just a second. Let me jump back to the previous line. Valence electrons. You need to know that because we're going to start talking about what valence electrons do in a few slides. And what time is it? Oh, I think we'll get to it. But valence electrons are the ones that are in the outermost shell. You see in the picture down below, the gray is the nucleus, so that's the protons and the neutrons. Oh, here's one for you. Hydrogen has the atomic number 1, right? So you know it's got 1 proton and one electron. Hydrogen also weighs just a little over 1. Okay, so hydrogen has the atomic mass of 1 and some change, right? That's the electrons. So what does that say about hydrogen in terms of subatomic particles? What subatomic particles do you find in hydrogen? Or what subatomic particles do you not find in hydrogen, based on the fact that a hydrogen atom weighs 1 and some change? Yeah, doesn't have a neutron, does it, Tim? It weighs 1 and change. The change of the electrons, the one's the proton. There is no neutron. Hydrogen's unique that way. It doesn't have any neutrons, okay? So a lot of other atoms change the number of neutrons like we were talking about, all right? Now, in the case of hydrogen, how many valence electrons does it have? That outermost shell, by the way, is also called the valence shell. So look at hydrogen. There you go. How many valence electrons in phosphorus? I'm going to count myself to make sure. How many in carbon? Raymond, remember, it's not all of the electrons, just the outermost or the valence. Carbon's got 4. There you go. See how that works? Yeah. The outermost shell is the valence shell. Now, the reason why I emphasize that and point that out is we're going to talk about bonding here in a second, or in a bit. And bonding is going to occur, in some cases, is going to occur using those valence shells. So now you got an idea what they are. And we've got questions on that. Okay, few years back, some hikers were in the woods up in, I don't know, Switzerland, Austria, someplace like that. They come across a dead guy. All right, well, okay, obviously some hiker who succumbed. All right, Caitlin, take care. All right, so this guy died up in the mountains, obviously, and being up in the mountains and in Europe and so on and so forth, he had frozen. And when the hikers came upon him, though, the funny thing about it, or the strange thing, was he wasn't really dressed the way you would expect a modern human to be dressed. He was dressed in skins, furs, he's carrying an arrow and quivers, all handmade. None of this he bought at Sports Authority, right? So even though it was in modern times, this guy was dressed like he was from some other time, right? So space traveler. Right, we could use our reasoning to come up with is that a reasonable hypothesis? Space traveler, you're walking in the woods and you find this dead guy and he's dressed in skins. No, of course not. Could be, but it's not. All right, so what's the thing with this guy? Well, there had been a local warm-up period that was occurring in this area, and this fella who had died, I'll tell you in just a moment, some time ago had gotten frozen in ice, and when the ice melted because of the warm-up period, his body froze out of the ice, and they're walking along, and they find him. So that's how they found this guy. Now, what they do is they found out this guy died, I don't remember exactly what it was, but something like 5,000 years ago, right? This guy died, and it's so cool because they actually, because the ice preserved him, they could get in his stomach, and they could tell what he ate right before he died, and even know where he got what he ate. He ate these berries, and there was only one place coming up the trail, which had been there for eons, that went by this berry bush. That's kind of cool. They knew what berry bush he ate from. Had to eat from that one. So this guy, this guy's dead, and he's decomposed a little bit. Yeah, right, but the ice helps keep him frozen. But how do they know he's been dead 5,000 years? Well, the way it works in your body is most of the carbon in your body is carbon-12. But because the world and the universe has some carbon-14, you also have some carbon-14 in your body. Now, don't worry about being radioactive. By the way, there's a term for the isotopes that are radioactive. Those that are radioactive are called radioisotopes, radioactive isotopes. Not every isotope is radioactive. Carbon-14, for example, is. Now, radioactive means that an element is unstable, and that means it disintegrates. All right, I don't want to get into the physics of it, but that's how nuclear power plants work. They take an element that's unstable. When it falls apart, energy is released. No, not number of protons, number of neutrons. Number of neutrons, Raymond. Protons changes the element. So when these atoms that are unstable, there you go. When these atoms are unstable and fall apart, they release energy. Again, I don't want to get into the physics of this, but that happens in radioactive isotopes. Because having those extra neutrons, they're unstable. And obviously, I'm not talking about it in a psychological term. Mother Nature likes things in balance. She likes things stable. So there's a natural tendency for things that are unstable to decompose. Got it, right? So when you die, you no longer bring in carbon. You're dead. Now you're thinking, what do you mean bring in carbon? I don't need carbon. Yeah, you do. You eat, glucose. That one we did the ratio on, that has carbon. Food has carbon. Plants bring in carbon when they photosynthesize, which we'll talk about later on. But yes, you're a carbon-based life form. You bring in carbon from the outside environment. So some of that carbon is carbon-14, but when you die, you no longer bring any carbon, right? You're dead. Okay, fine. Let's take a look at how that works then. I'm going to use a graph to show you this. Down on the x, which is which variable? The time before present, the half-lives on this, is that the independent or the dependent? You can look at the y-axis, fraction of isotope remaining in fossil. You'll see what I mean in just a minute. So the x-axis, the time before present, Raymond, you're saying it's the independent. There you go. Now let's word it out. The fraction of isotope, I don't know what that means, but it talks about a part of something. Is that dependent on time, or is time dependent on that fraction of something? You could almost look at this graph and say, what if time was time in years, and instead of fraction of isotope, which might be throwing you off, let's say height in humans. So does height depend on how old you are? Or does how old you are depend on your height? Which one makes sense? Of course. So in this particular case, time is the independent, right? And that's because the fraction of the isotope remaining in the fossil is dependent upon it. Now, what the heck does that mean? All right, you die. When you die, you have you have all of the carbon-14 you're going to have. So in this particular thing where it says 1 and 0.9, think of those as percentages. So when you die, all of the carbon-14 you've accumulated up to that point when you die, you have 100% of it. As you die, since you're no longer bringing in any more, it begins to change. It becomes unstable. It falls apart. So the carbon-14 is decreasing, right? Unstable elements, radioactive things, when they get rid of these extra particles, that's what they do. They throw off neutrons. When they do that, they decrease in amount. Like, for example, certain radioactive elements, when they decompose, become other elements with time. That's how an element can change, by the way. So what we're saying in here is just the carbon-14 isotope is decomposing, and it's doing it from the time you die up until when these guys come along and find you. All right, now, it's a clock, right? It's a clock. We know that it takes, look at the y-axis, 50% of the carbon-14 in your body that you had when you died to be gone in 5,730 years. See what I mean? That's called a half-life. Radioactive elements have a half-life, and it does exactly what it says. A half-life is the amount of time, see, that's lives, for half of the element to decompose. Okay? Does that make sense, Raymond? So a half-life is how long does it take for, remember, look at the 1x is more in percentages. How long does it take for 100% of the carbon-14, the day that that old fella dies, how long does it take until if you sampled his dead body, because he's not bringing in carbon anymore, but how much of that carbon-14 is left? In 5,730 years, about half. Now that happens every 5,730 years, that halving. So in another 5,730 years, he'll have half of a half or a quarter. And in another 5,730 years, he'll have an eighth, and then a 16th, and a 32nd, and so on and so on and so on. It's asymptotic, right? It gets smaller and smaller, never reaches zero. Does that make sense to you guys? Because I want to ask a question. All right, so tell me how they knew this guy was dead, let's say 5,730 years. What did their analysis tell them that let them know this guy had been dead around 5,000, 6,000 years? Okay, so you're a scientist. How long has this guy been dead? You take a sample of his body, little tissue, right? There you go, Tim. So you take a little sample of his tissue, and you run it through a machine, and the machine comes back and it says, oh, fraction of isotope remaining in fossil, 0.5. So you go over to your little chart, you go, oh, so the machine just told me only 0.5 is left. I go here. Thank you, pen. I go here, and I go, one half-life. I know this is carbon-14, and carbon-14 has a half-life of 5,730 years. Now, let me ask you a question. What if the machine came back with the value 0.25? So this one here. How long has the guy been dead? There you go. How'd you get that, Tim? This chart helps, obviously. There you go. 2 half-lives. Okay, makes sense to everyone? To you two that are left. Thank you. All right, now we're going to step into a little bit of atomic structure. I don't get too far into atomic structure because it gets real heady. Trust me, folks. So I just need to explain enough so you have some basic idea of terminology and the names of parts, okay? Oh, by the way, before I go on with half-life, 5,730 years is only for carbon-14. Each radioactive isotope has its own half-life. I think like uranium's half-life is 20,000 years. That's the problem with uranium waste. When they take uranium waste out of a nuclear power plant, it's still radioactive. It's just not radioactive enough to, it's like the battery. The battery might not officially be dead, but it's so low on power it can't do anything. So they bury that radioactive stuff in the ground. It's still deadly radioactive. And with a half-life of 20,000 years, that stuff's going to be around a while. So that's the problem with nuclear wastes. Okay, ready for atomic structure. Clear your heads and let's take a look. All right, so on the left, starting over here, is the picture that we saw in the previous slide, right? We're going to play with the element neon. Neon's got the atomic number 10. So, of course, and we're not going to worry about neutrons here. We're going to start moving in here in just a second to talking about properties of electrons, bonding. Neutrons are important, don't get me wrong, but as far as biology and the level that we're going to talk about it, neutrons are, we're just going to kind of ignore them. Kind of like we ignored electrons for weight and mass because they don't weigh very much. We are going to pay attention to electrons now, but there's neon. Neon's got 10 electrons. Neon has 2 shells. So in this case, the second shell would be the valence shell and would have 8 electrons. Now look at the first shell, though, versus the second shell. There's a difference between them. How many electrons do you see in that first shell? And electrons, again, are the little yellow dots. Yeah, there you go. How many in the second shell? Okay, now let me blow your mind for just a second. Shells are artificial. That drawing that you see there of neon is called the Bohr representation. Not to bore you, but named after a Dutch physicist named Niels Bohr. He is credited, or it's called the Bohr representation, because he used it as a way to help people understand atomic structure. It's not really how it looks. That's what I mean by shells are artificial. Shells are artificial, just like mammals are artificial, right? Those are artificial constructions. Let me show you what I mean. If we look in the first shell, the one that's only got 2 electrons, what is real in the shell is something called an orbital. And if you're looking at this orbital, now the 1 means it's in the first shell, and the S means that it's spherical in shape. What does he mean spherical in shape? Remember, electrons occur in a cloud. Remember? So and because of the dual nature of matter, they occur as a particle in a cloud. So that orbital that you see there is actually an electron cloud. Imagine the nucleus right inside the middle. Now the first shell only has 1 of these little tiny S-shaped orbitals. If we go to the second shell, we're going to stop right there because of course it goes on as atoms get bigger. But the second shell has got a 2s orbital, which notice is a little bigger, right? Because if you look down below, the 1s is going to fit inside the 2s. And it's also got these other electron clouds, or what they call probability clouds, that are shaped like dumbbells. Notice that the X, Y, and Z is letting you know that we're in a 3-dimensional world here, right? So in the X dumbbell-shaped orbital cloud, there are electrons. In the Y and in the Z. Now, folks, no matter what shape the electron, whether it's S or P, whether it's a dumbbell or round, all orbitals are restricted to holding only 2 electrons. 2 electrons per orbital. Now, electrons, a nice way to write electrons, shorthand-wise, is E with a superscript minus. I'll give you a hand when you take your notes. So, no matter the orbital, no matter the X, Y, the Z orbital, no matter the S versus the dumbbell shape, no matter what, you're only going to hold 2 electrons. So now if we look at the neon atom down below in part C, the superimposed, we can say that there are 2 electrons in the 1s. There are 2 electrons in this bigger 2s, and then there's 2 here, 2 here, and 2 here, right? Piece of cake, huh? All right, now what if I had the next element up? Sodium. Sodium has got 11 electrons. Where's that next electron going to go? Where's that 11th electron? What are we going to have to add in order to put that next electron in there for sodium? Yeah. If I added, let's say I added a proton to make it sodium. Another dimension, what kind of dimension? Another S, Tim. It'd be a 3s, right? Third shell. Now, if you remember doing electron configurations in chemistry class, this is that 1s2, 2s2, 2p6, 3s2 stuff. And if you're going, holy cow, then don't worry about it. All right, I got a few minutes left, so there are some things I want to finish up. Everybody clear on shells, right? We know what... Now, as I said, shells don't exist. Orbitals make up shells. That's why this is collectively known as the second shell. So electrons are physically in an orbital, that cloud, and then shells are just collections of orbitals. And Niels Bohr drew them out so that we could understand them easier. Thank you, Niels. Okay, now there's a relationship between what shell an electron is in, whether it's in the first shell, the second shell, third shell, fourth shell, so on, and the amount of energy it has. This is important because this is where that chemistry to biology link begins to occur. This is going to become very important in, in respiration and when we talk about photosynthesis. So here's just a portion of an atom. There's the atomic nucleus. There's 3 shells in this particular picture. What we say is that an electron in a lower energy shell is going to be found, or an electron of lowest energy is going to be found in the first shell. If you have a little bit higher energy, you're going to be found in the next shell. If you have an even higher energy than that, you're going to be found in the third shell. So the electrons here in this first shell, they don't have as much energy as the ones here and the ones here. Now, electrons can move between shells. You see the arrows? But they can only do that when they absorb or lose energy. If an electron in the first shell wants to jump to the next shell, it needs to absorb some energy. And then if an electron from the third shell falls down to the second shell, or even the first shell, it's going to lose that energy. Now, we'll talk more about energy later on in the laws of thermodynamics. But you see, what this basically says for us, biologically speaking, is that atoms, they can kind of act like batteries. They can store energy. So here's another picture showing the same thing. So now the shells have letters. Sometimes they don't give them numbers. They give them letters, K, L, M, and N. But same idea. As you move away from the nucleus, the amount of energy necessary to reside in the L or the M or the N shell has to increase. Okay, now I'm going to finish the lecture with something that's going to help you take all of this physics, theory stuff and put it to real life. Let's talk about glow-in-the-dark paint. Let's talk about one of Cooper's favorite toys is a glow-in-the-dark ball. Go outside and play it and throw it. He loves that. In order to get that glow-in-the-dark ball to work, I put it under a lamp for a while, right? Okay, let's talk about how glow-in-the-dark paint, or the molecules that make up glow-in-the-dark paint. Now, not every molecule does this not every atom does this energy jumping as readily as others. There are some atoms that are much more prone to do that. Those that make up glow-in-the-dark paint happen to be one of those. So when the light shines on the glow-in-the-dark ball that I use of Cooper's, before I go outside, what I'm doing is this part. The little squiggly line is supposed to be light energy. So that's the energy from the lamp. And, I'm sorry, wrong side, excuse me. It's this side. So as I'm taking the glow-in-the-dark ball and putting it on the lamp, the electrons in the atoms that make up the molecules of the paint, the glow-in-the-dark material, not necessarily the paint, are absorbing energy. Those electrons are moving up to higher energy levels. The light from the light that's shining on there, the energy in the light is taking electrons from the K, jumping them to the L. Everybody's moving up, right? Everybody's moving up because guess what? We got more energy now. Turn the light off or take the ball outside, and the glow-in-the-dark ball eventually gets dim. Why? Because for every plus, there's a minus. For every up, there's a down. For every time energy is absorbed, the equal amount has to be released. So when Cooper's ball out in the dark, what it's doing, those electrons in those atoms, in those molecules, in that glow-in-the-dark material is losing energy. And that energy is what you see as the glow. That's what's causing the glow. So right there is a direct indication in your everyday life of the fact that of atoms can store and release energy by their electrons. Now, if you're thinking electrons can move partly between like the K shell and the X shell, they can't. And that's a function of quantum mechanics. You either have to be in the K or the L, or the M or the N. You can't be halfway in between, or even partway in between. All right, folks. Let me stop the recording.